Have you ever found yourself staring down a complex, dense academic chapter, feeling that familiar sense of overwhelm, wishing there was a real shortcut to not just read it, but to truly get it?
Uh-huh.
To feel genuinely deeply well-informed without getting lost in the weeds?
Yeah, I think we've all been there.
If that sounds familiar, then you are absolutely in the right place. Welcome to the Deep Dive, your personal guide to navigating dense information and extracting those profound, actionable insights that truly stick.
And today, we're plunging into a topic that is just absolutely foundational to organic chemistry. Aromatic substitution.
Okay.
This is just some niche area. It's one of the most fundamental, versatile, and mechanistically rich transformations we know. Truly, if you want to understand how we build and modify complex molecules from the pharmaceuticals that heal us to the advanced materials that define our technology, this is where it all begins.
Our journey today is a comprehensive exploration of an authoritative source. Chapter 9, Aromatic Substitution, from Advanced Organic Chemistry, Part A, Structure and Mechanisms, 5th ed.
The classic text.
Exactly. And when we say deep dive, we mean it. We're not just skimming. We're going to pull apart the foundational mechanics, dissect surprising experimental evidence, and illuminate the practical applications that underpin real-world synthesis and analysis. Think of it as a custom-tailored shortcut to becoming fluent in the language of molecular transformations.
That's our mission. Over the next 20 to 30 minutes, we're going to meticulously unpack core structures, intricate reaction mechanisms, key concepts, compelling experimental examples, and even the subtle interpretations of diagrams, which, of course, for an audio format we'll describe so you can visualize them clearly. We'll define all the technical terms in plain language and connect them to real-world applications, ensuring you gain a thorough yet accessible understanding without feeling overwhelmed by the textbook itself.
Okay, let's unpack this. We're kicking off our deep dive with electrophilic aromatic substitution, or EAS. Now, for anyone interested in making new compounds or even just understanding how chemical reactions fundamentally work, this is a huge deal. It's a core transformation in organic chemistry.
It really is. Think of EAS as one of the most elegant ways to introduce a new chemical group onto an aromatic ring, or even swap out an existing one.
Right.
Its importance isn't just about the sheer variety of molecules you can synthesize, which is, a massive boon for chemists. What's equally significant is that EAS reactions are among the most thoroughly studied classes of organic reactions from a mechanistic point of view.
Okay.
This means we have an exceptionally deep understanding of how these reactions unfold at the molecular level, far beyond simply knowing what goes in and what comes out.
And when we talk about what can attack these rings, it's not just one type of molecule. The field is vast.
Oh, absolutely.
While we typically imagine replacing a hydrogen atom, our source points out that other groups like silicon or mercury can also be displaced.
Indeed. And to help you navigate this vast landscape of potential attackers, our source, Advanced Organic Chemistry, provides a really useful categorization of these electrophiles based on their reactivity. It's like a tiered system for how aggressive they are.
Okay, a reactivity scale.
Pretty much. First, we have what's called Group A. These are your heavy hitters, the highly reactive electrophiles that can attack almost any aromatic compound, even those that have strong electron withdrawing groups. We call them EWGs, which usually make rings less reactive.
Right, those make it tough.
Exactly. Think of the nitronium ion, NO2 plus NOR, a powerful species typically generated when you mix nitric acid with concentrated sulfuric acid.
The classic nitrating mix.
Yep. Or consider various carbocations, those positively charged carbon species often formed when alkyl halogens react with a Lewis acid, like aluminum chloride. These electrophiles are so potent, they can often overcome significant electronic obstacles.
So these are the ones that can blast through pretty much anything, even a reluctant ring.
For practical purposes, yes, they're incredibly potent. Then we move to Group B. These are moderately reactive. They readily engage with simpler aromatic compounds like benzene itself, and also with rings that already have electron-releasing groups, ERGs, which are known to activate the ring.
So they need a bit more help or an easier target.
Kind of, but you generally won't see them reacting with those tougher EWG-substituted rings. Common examples here include complexes like bromine bonded to a Lewis acid, or acylium ions, which are generated from acylamides reacting with Lewis-SS acids. These are your workhorses for a broad range of reactions.
And finally, Group C, which sounds like the pickiest group of all.
You got it. These are weakly reactive electrophiles. They're so discerning that they'll only substitute highly activated aromatic compounds, those that are already significantly more reactive than benzene.
Okay.
The nitrosonium ion, NO plus air, or aryl disonium ions, ARN2 plus PAS, fall into this category. This categorization is incredibly valuable. It gives you a quick reference chart, a general guide to understanding the feasibility of any given EAS reaction, helping you anticipate what kind of ring you're dealing with and what kind of electrophile it might react with.
What's truly fascinating here, and I think this is a huge aha moment, is that despite this seemingly endless cast of characters and a vast array of aromatic systems, the source reveals a single, elegant truth. What is it that fundamentally ties almost all these EAS reactions together, transforming how we view them?
It's the incredible insight that almost all electrophilic aromatic substitutions follow a unified three-step dance.
A three-step dance. I like that.
Yeah, think of it like a universal choreography that explains everything from a simple nitration to a complex acylation. This isn't just about memorizing steps, it's about a foundational understanding that suddenly makes hundreds of seemingly disparate reactions logical and deeply connected. While the specific rates and energy profiles might vary, the core sequence of steps and the nature of the intermediates remain remarkably consistent. This allows us to talk about EAS in a generalized, powerful framework.
So let's break down this universal mechanism step by step, starting with step 1 pi, complex formation. What exactly is the very first interaction between our aromatic ring and that incoming electrophile?
This is the initial, rapid, and often reversible complexation of the electrophile with the electron system of the aromatic ring. Imagine the electrophile briefly sniffing out or interacting with the electron cloud that hovers above and below the aromatic ring.
Okay.
It's what we call a donor-acceptor complex, where the electrons of the aromatic ring act as the donor, lending a bit of their electron density to the electrophile, which acts as the acceptor. This complex is typically formed quickly and can fall apart easily, showing modest stability.
And the source mentions some truly intriguing structural data here, drawn from cutting-edge techniques like X-ray crystallography, right? That's really peering into the molecular architecture at an atomic level.
It is, and it's quite revealing. For example, groundbreaking X-ray crystallography studies conducted at incredibly low temperatures have given us a stunning glimpse into these initial interactions. They've shown that when molecular bromine, Br2, complexes with a molecule like benzene or toluene, the Br2 doesn't just float vaguely over the ring. Instead, it positions itself almost perpendicular to the aromatic ring and is located precisely between two specific carbons.
Wait, between two carbons? That's not what I'd intuitively picture as the start of a reaction. I'd imagine it just sitting over the whole ring.
Exactly, and it gets even more detailed. For toluene, two distinct complexes have actually been identified. One where the Br2 is associated with the ortho carbons, and another where it's with the para-carbons.
No kidding.
This is incredibly significant because it suggests that the positional selectivity, the preference for where the electrophile ultimately attaches, might actually begin at this very earliest complex stage, even before any new chemical bonds are fully formed. The molecule, in a sense, starts making its choices right at the first greeting.
So the molecule is already deciding where to go before the main chemical event. What about other examples that shed light on this first step?
Consider the mesitylene NO+ complex. Here, there's such substantial charge transfer that it effectively behaves like a complex between the aromatic radical conformation and the neutral NO molecule itself, with the NO sitting centrally relative to the ring.
Interesting.
And recent sophisticated computational studies of benzene nitration have shown that the nitronium ion, NO2 plus AN, initially approaches the midpoint of a carbon-carbon bond, not the very center of the ring. All these details paint a more complex, dynamic, and pre-organized picture of that first fleeting interaction than we might have initially imagined.
Okay, that's step 1, the initial handshake. Now, step 2 is where the actual chemical bond forms, the sigma complex formation. This sounds like the critical intermediate in the whole process.
It truly is.
Yeah.
This is the stage where the carbon at the site of substitution in the aromatic ring forms a brand new sigma bond and is now directly connected to both the incoming electrophile and the hydrogen atom that will eventually be displaced. This crucial intermediate is known as the cyclohexadenalium carication, sometimes also called a Wieland intermediate.
And the source highlights its electronic characteristics, describing it as a 4-electron delocalized system, electronically equivalent to a pentadienyl location. What does that mean for how it behaves, for its stability?
This is a critical point. It means the crucial cyclic aromatic conjugation is temporarily broken. That highly stable, fully delocalized aromatic system has been disrupted.
Ah, okay, so it's lost its special stability.
Temporarily, yes.
Yeah.
As you might expect, this is a higher energy state compared to the original aromatic ring because you've interrupted that very stabilizing aromaticity. When we look at simple molecular orbital theory or draw resonance structures, it becomes clear that the positive charge in this intermediate is predominantly located at the positions ortho and para to the site of substitution.
Ah, so this is directly linked to why some substituents direct electrophiles to ortho and para positions later on, and others to meta. The charge distribution in this intermediate is literally setting the stage for where the next group can or can't go.
Precisely. It's a foundational insight that explains directing effects. The positive charge accumulates at those specific ortho and para sites. If an electron-donating group is already there, it can help stabilize that charge, making those positions more receptive to attack. Conversely, if an electron-withdrawing group is present, it will destabilize those positions even further, making attack there less favorable. There's also an active debate in the field about whether, for some reactions, an electron transfer actually occurs before this full spawn formation, leading to a discrete Kekulé radical pair.
Okay.
This could potentially influence the final isomeric product composition in subtle ways.
So from this higher energies complex, we move to step 3, deprotonation. This is where the molecule gets its aromaticity back, right? It sounds like a sigh of relief for the molecule.
That's a perfect way to put it. In this final step, the hydrogen atom at the site of substitution is removed typically by a weak base present in the reaction mixture, and the electrons it leaves behind are used to reform the aromatic system. This leads to the re-aromatization of the ring and the formation of the stable substituted product.
Right.
Now, it's important to note that the formation of this complex can be reversible. Its ultimate fate, whether it continues forward to product or reverts back to reactants, depends on the relative ease of eliminating the incoming electrophile versus eliminating that proton.
Makes sense.
For most electrophiles, especially the highly reactive ones in Group A, proton elimination is much easier, making the psi complex formation essentially irreversible under typical conditions.
And usually, forming this complex is the rate-determining step, which dictates the overall speed of the reaction. But you mentioned earlier that's not always the case.
That's right. While complex formation is typically the rate-determining step leading to predictable kinetics, there are indeed exceptions. In certain scenarios, other steps, like the initial formation of the electrophile itself, or even the final deprotonation step, can become rate-limiting. This leads to different observed reaction profiles and is a key area of mechanistic study.
This general three-step mechanism makes a lot of sense conceptually, but how do chemists actually know this is really happening? What's the experimental proof that backs up these theoretical steps and fleeting intermediates?
Excellent question. This isn't just theory. It's supported by a wealth of compelling evidence gathered over many decades of meticulous study. Let's look at nitration as a prime example because it's one of the most thoroughly investigated EAS reactions. Kinetic studies famously show that the active electrophile in many nitration reactions isn't nitric acid itself, but rather a tiny, highly reactive species called the nitronium ion, NO2 plus Cas.
And the source explains its formation. Nitric acid reacting with concentrated sulfuric acid to produce the nitronium ion, hydronium, and bisulfate.
Exactly. And this isn't just a hypothesis. Scientists have actually detected the nitronium ion spectroscopically, using techniques like Raman spectroscopy.
Oh.
Even more impressively, you can prepare stable nitronium salts, like NO2 plus BF4, nitronium tetrafluoroborate, which are solid compounds that you can isolate and then use directly as nitrating reagents. This direct detection and isolation absolutely confirm its existence and its critical role in nitration.
So we know what the active electrophile is, but how do the reaction kinetics, how fast or slow a reaction goes, help us understand the steps of the mechanism?
Kinetics offer crucial insights into the rate-determining step. For aromatics of moderate reactivity, nitration typically exhibits what we call second-order kinetics. This means the reaction rate depends on the concentration of both the nitrating reagent and the aromatic compound.
Okay.
This tells us clearly that the attack of the electrophile on the ring, the formation of that complex, is the slow rate-limiting step. However, for very reactive aromatics like mesitylene, something fascinating happens. The reaction can become so incredibly fast that the generation of the nitronium ion itself becomes the bottleneck. In those cases, you observe zero-order kinetics in the aromatic compound, meaning the reaction rate is completely independent of the aromatic's concentration. Different reactive aromatics will all nitrate at the same rate, essentially limited by how quickly the nitronium ion is formed.
Okay, so the supply chain is the problem there, not the factory.
Exactly. This really highlights the importance of identifying the active electrophile and understanding how its generation can impact the overall rate, even overriding the reactivity of the aromatic substrate itself.
Here's where it gets really interesting and incredibly clever. The use of isotope effects. This is such an ingenious way to probe the rate-determining step, isn't it?
It's one of the most powerful tools in mechanistic organic chemistry. The logic is elegant. If the removal of the CH bond, that final proton loss step, were part of the rate-determining step, you'd expect to see a primary kinetic isotope effect.
Right.
This means if you replace the hydrogen at the substitution site with its heavier isotopes, deuterium D or tritium T, the reaction rate should slow down significantly. KH-KD1, where KH is the rate with hydrogen and KD is the rate with deuterium. This is because breaking a CD bond is inherently slower than breaking a CH bond.
And the reality for most EAS reactions, like nitration of benzene or toluene.
Crucially, for most nitration and halogenation reactions, you observe no primary isotope effect. The rates for protium-containing compounds and their deuterated or tritiated counterparts are essentially identical. KH-KD1.
So almost no difference.
Exactly. This is incredibly significant because it tells us that the proton loss step is not rate determining. It's a fast step that occurs after the rate determining step. This observation powerfully supports the existence of this complex intermediate. The slow step is the formation of this intermediate, and then the proton is quickly removed in a subsequent rapid step, leading to the final aromatic product.
But the source notes some exceptions, right? Sometimes you do see an isotope effect.
Yes, and these exceptions actually add nuance to our understanding rather than invalidating the general mechanism. Some EAS reactions do show modest isotope effects, with KHKD values typically between 1.2 and 2.0. This suggests that in these cases, proton removal can be partially rate-limiting, meaning it's contributing to the overall slowness, but isn't the only slow step.
Okay.
And in a few rare cases, the isotope effect is quite large, indicating that the deprotonation is indeed the fully rate-limiting step. These variations are perfectly compatible with the general three-step mechanism, just representing different points on the energy landscape, influenced by specific reaction conditions or molecular structures.
Another piece of compelling evidence, and this feels almost magical, is the actual observation of stable sigma complexes. This means these fleeting intermediates aren't just theoretical constructs, but can actually be caught and studied.
It's truly a testament to the advancements in analytical chemistry. Under what we call stable ion conditions, typically involving superacids and extremely low temperatures to suppress side reactions and stabilize charges, substituted cyclohexadienyllium ions can be directly observed and characterized by NMR spectroscopy.
Amazing.
For instance, the protonation of fluorobenzene by a superacid or specific alkylation products of benzene derivatives have been meticulously studied this way. This direct observation provides irrefutable proof that these intermediates are chemically feasible species, even if they are short-lived under normal reaction conditions. It's like catching a glimpse of a rare, elusive creature in its natural habitat.
That's phenomenal. And then there are trapping experiments, which sound even more direct, like chemists are literally catching these intermediates.
Trapping experiments are a beautiful, indirect way to infer the existence of short-lived intermediates. One classic example involves treating a specific acid, let's call it compound 1, with bromine. Instead of simple substitution, you observe the formation of a cyclized product, a lactone, compound 2. This happens because an internal nucleophile, a carboxylate group within the same molecule, actually traps this complex as it forms, preventing its usual deprotonation. This forces a different reaction pathway, providing direct evidence for this complex's transient existence.
So the molecule essentially reacts with itself to prove the intermediate exists. That's elegant.
It absolutely is.
Yeah.
Another illuminating example comes from the nitration of certain alkylated benzenes like compound 3 in a solvent like acetic acid. Here, the product, compound 4, shows that acetate, acting as an external nucleophile, has trapped this complex.
Ah.
This is particularly likely when the electrophile attacks an already substituted position, what we call ipso attack, because that blocks the easy, usual deprotonation pathway. When that normal route is blocked, it gives an external nucleophile a chance to intervene and capture the intermediate, providing further concrete proof of its formation.
So all this evidence really locks down the general three-step mechanism for electrophilic aromatic substitution. But now we shift to something vital for organic synthesis: How do existing groups on an aromatic ring influence where the next group goes? This is the concept of directing influence of substituents.
This is where structure-reactivity relationships come into play, and they've been studied intensely since the 1870s. Early on, chemists observed clear patterns. Substituents were either activating the ring and directed the incoming electrophile to ortho-para positions, or they deactivated the ring and directed to meta positions.
Right, the classic orthopara versus meta-directors.
Exactly. The deeper understanding of why this happens became clear with the development of concepts like electron interactions, resonance theory, and later molecular orbital theory.
Let's start with those activating orthopara OP directing substituents. These are like the friendly neighbors, right? They make the ring more welcoming and point the newcomer to specific spots.
Yes, exactly. These are electron-donating groups, or ERGs. Think of common examples like alkyl groups, such as methyl or ethyl, or even more powerfully, atoms directly attached to the ring that have an unshared pair of electrons, like the oxygen in AOH or OCH3, or the nitrogen in NH2.
Yeah, the strong activators.
How do they work? They stabilize the transition state that leads to complex formation. They achieve this stabilization primarily through resonance and hyperconjugation. These effects help to spread out or delocalize the positive charge that develops in this complex, particularly when that charge lands at the ortho and para positions relative to the substituent. This makes attack at those positions energetically much more favorable.
And the source mentions that for these activating groups, the Hammett equation, which is essentially a way to quantify how different groups influence reaction rates, often correlates best with something called sigma plus substituent constants. What does that plus tell us about how these groups work?
That plus is key because it specifically highlights how important direct resonance interaction is. It tells you that these groups are particularly good at sharing their electrons directly with that developing positive charge in the transition state, stabilizing it powerfully.
Okay.
This is exactly what these ERGs do when the positive charge is forming at the ortho and para positions. So when you see a good correlation with SUF plus ake, it's a strong indicator that resonance is playing a dominant role in the substituents effect.
All right. What about the deactivating meta-directing substituents? These sound like the less friendly neighbors who make the ring less reactive overall.
Precisely. These are electron-attracting groups, or EWGs. Common examples include a carbonyl group directly attached to the ring, like in a ketone or aldehyde, or highly electronegative elements without an adjacent lone pair that can resonate, such as a nitro group, NO2, or a thiano group, AVN.
Got it.
They actually retard electrophilic substitution, making the ring less reactive overall. They destabilize the I complex, especially when the positive charge is concentrated at the ortho and para positions. Since the meta positions are less destabilized, though still deactivated compared to benzene, electrophilic attack predominantly occurs there, simply because it's the least unfavorable option.
And then there's the famous halogen anomaly, deactivating but still ortho-para directing. That sounds like a contradiction in terms. How can it be both?
It's a fascinating one, and it's a result of two opposing electronic influences playing tug-of-war. Halogens are more electronegatives than carbon, so they exert what we call an inductive effect. They pull electron density away from the ring through the sigma bonds. This electron withdrawal reduces the overall electron density in the ring and specifically opposes the development of positive charge during the reaction, thus reducing the overall reactivity towards electrophiles. So yes, they deactivate the ring, making it slower to react.
But they still direct to ortho and para positions despite being deactivating.
Yes, and this is where the second effect comes in, resonance. Halogens also possess unshared electron pairs, those lone pairs that can be donated into the aromatic system through resonance. While this resonance donation isn't strong enough to make the ring more reactive overall, it does preferentially stabilize the ortho and para transition states through that resonance. This resonance stabilization outweighs the unfavorable inductive effect at those specific positions for directing the attack.
I see.
So for halogens, the overall deactivating inductive effect dominates the rate of reaction, but the OP-directing resonance effect dictates the regioselectivity where the new group ends up. It's a classic example of competing effects.
This is where molecular orbital theory, or MO theory, comes in, right? It sounds like it can give us an even deeper understanding of these subtle electronic effects.
It absolutely does, by allowing us to look at the electron distribution within the molecules and intermediates at a more fundamental level. When discussing substituent effects, we can focus on how they influence either the complex itself or the initial aromatic reactant. According to Hammond's postulate, for reactions with a high activation energy and a late transition state, meaning one that closely resembles the complex intermediate, We focus on the stability of that intermediate.
So in a late transition state, the subcomplex is key. How do the MOs explain things then?
In that complex, as we discussed, the positive charge is predominantly at the ortho and para positions. Molecular orbital analysis shows that the LMO, the lowest unoccupied molecular orbital, has its largest coefficients essentially, the most available space for electrons at these ortho and para positions.
Okay.
Electron-releasing groups, ERGs, stabilize these positions most effectively by donating into these orbitals, effectively spreading out that positive charge. This favors ortho-para substitution. Conversely, electron-withdrawing groups, EWGs, destabilize these positions by pulling electron density away, making attack at the meta position, where there's less positive charge buildup in the intermediate, the least unfavorable path. This MO interpretation aligned perfectly with the qualitative resonance arguments we just covered.
What about highly reactive electrophiles, those with an early transition state? How does MO theory explain their behavior?
In that scenario, the transition state more closely resembles the reactant aromatic. Here, frontier orbital theory becomes more relevant. It predicts that the electrophile will attack the position with the largest coefficient of the highest occupied molecular orbital, H-hemo, in the reactant, essentially, where the electrons are most available and reactive.
Right, where the electron density is highest.
Exactly. For example, in anisole, and methoxybenzene, where the methoxy group is a strong air G, MO calculations beautifully show that it raises the energy of the HOMO and concentrates electron density specifically at the ipso, ortho, and para positions. Both the HOMO coefficients and the overall charge distribution correctly predict preferential ortho and para attack, perfectly confirming the Irigi effect.
But the source notes a potential pitfall with EWGs and relying solely on frontier orbital theory. Can you explain that nuance?
Yes, this is an important point for your critical understanding. For electron-withdrawing groups like a nitro group, while they lower the energies of the orbitals overall, the HOMO distribution might still show the highest coefficients at the para position. If you only used frontier orbital theory, you might erroneously predict para substitution for these unreactive rings. However, for deactivated rings, the reaction typically has a higher activation energy and thus a later transition state. Therefore, considerations of the stability of this complex are actually more appropriate for these cases, and those calculations correctly predict meta-substitution. It's a great example of needing to choose the right theoretical model for the right reaction scenario.
And MO computations can go even deeper, right? Using something called reactive hybrid orbitals?
That's right. More advanced molecular orbital methods use what are called reactive hybrid orbitals. These are sophisticated constructs that combine contributions from all MOs to better predict reactivity at each specific site on the ring. The properties of these orbitals, which can be computed based on how much energy is released when a proton interacts with the various carbons, correlate remarkably well not just with positional selectivity, but also with the relative reactivity of different aromatic compounds.
So they're quite predictive.
Very much so. For instance, the source includes a graph showing how the computed energy of interaction for these orbitals aligns nicely with experimental partial rate factors for diverse reactions, like mercuration, nitration, and chlorination, demonstrating the predictive power of these advanced computational tools.
What about those substituents that aren't directly attached to the ring, but still manage to have an electron withdrawing effect, like a nitro group that's part of an alkyl chain attached to the benzene ring?
Even those distant electron withdrawing groups can exert a significant influence. Our source gives examples like a nitylichi CH2NO2 group or eladushi ETL3 group. While an alkyl group typically acts as an electron-releasing group, the strong polar effect that's the inductive withdrawal through sigma bonds from the remote EWG can effectively counteract and even overcome this electron release. This often leads to reduced electron density at the alkyl substituent itself, and the bond dipoles within the substituent itself further reduce the overall electron donation for the methylene group to the ring. The result: these substituents often lead to predominantly meta-substitution, as shown in the sources table listing percent meta-nitration for various alkyl groups bearing EWG substituents. It's a subtle but powerful effect.
So we've talked about the qualitative effects of these substituents. How do chemists quantify these influences? That's where partial rate factors come in, isn't it? This sounds like a really concrete way to measure reactivity.
Yes, partial rate factors are an absolutely crucial quantitative tool in EAS studies. They allow us to compare the reactivity of each individual position in a substituted aromatic compound to a single position on benzene. To calculate them, you first measure the overall rate of reaction of your substituted aromatic compound relative to benzene. Then you account for the statistical factors, for example. There are 2 ortho positions, 2 meta, but only 1 para position in a monosubstituted benzene, and distribute that observed reactivity proportionally among the different products formed.
And the source walks through a concrete example, nitration of toluene. Can you give us a sense of that calculation and what it tells us?
Certainly, if you observe that toluene nitration as a whole is 23 times faster than benzene nitration, and the product mixture is, say, 63% orthonitrotoluene, 34% paranitrotoluene, and just 3% metanitrotoluene, you can calculate the partial rate factors. For ortho, it would be around 43.5, for meta, 2.1, and for para, 46.9.
Wow, big differences there.
Exactly. These numbers vividly illustrate how toluene is significantly more reactive than benzene, particularly at its ortho and para positions, confirming the activating and ortho-para-directing nature of the methyl group. This kind of data gives us hard numbers to understand the subtle electronic dance.
What do these numbers, these partial rate factors, tell us about how picky a reaction is, about its selectivity?
They reveal 2 incredibly important things: reactant selectivity and positional selectivity. Reactant selectivity refers to how much the rate differs based on the overall ring substituent. Very large partial rate factors, especially for the para position, FP, mean high reactant selectivity. The electrophile shows a strong preference for reacting with certain substituted aromatics over benzene.
Okay.
Then there's positional selectivity, which is the preference for ortho, meta, or para-tac within the same molecule. This tells you where the electrophile likes to land once it chooses a specific molecule.
And there's usually a clear correlation between these 2 types of selectivity, isn't there?
Generally, yes, and it's a powerful generalization. High reactant selectivity is usually accompanied by high positional selectivity. In simpler terms, electrophiles that discriminate strongly between different reactant molecules also discriminate strongly between different positions on the same molecule. This means they'll typically show a low ortho-para ratio and negligible amounts of meta-substitution. Conversely, very reactive electrophiles tend to show low positional selectivity and low reactant selectivity, as they're less discerning overall.
So we can actually look at a table of selectivity data for different ES reactions and clearly see this spectrum of behavior.
Absolutely. If we use the para partial rate factor, FP, as a key criterion, since orthofactors can sometimes be complicated by steric hindrance, you can readily observe this spectrum. For instance, halogenation, particularly bromination, and Friedel-Crafts acylation typically exhibit very high selectivity with large FP values for toluene. This suggests a late transition state where the electrophile is very choosy. Protonation and nitration fall into an intermediate selectivity range, while Friedel-Crafts alkylation is a classic example of low selectivity, indicating a very reactive electrophile and an early transition state. This data is a powerful diagnostic tool for understanding the nature of the electrophile and the characteristics of its transition state.
So if we pull all these pieces together, what does this all mean? How do we interpret these quantitative relationships like partial rate factors and Hammett row values mechanistically?
It largely boils down to a fundamental concept in physical organic chemistry. The position of the transition state on the reaction coordinate, which is elegantly described by Hammond's postulate.
Okay.
Imagine the journey from reactants to products. If you have a highly reactive electrophile, the hump it has to climb the activation energy is small, and the transition state is early. It resembles the starting reactants more than the intermediate.
Okay.
At this early point, the positive charge that develops on the ring is small, so the interaction with the substituent group is relatively weak, leading to low selectivity. The electrophile just isn't very particular.
And for less reactive electrophiles, the opposite holds true.
Precisely. For less reactive electrophiles, the activation energy is higher and the transition state is later. At this point, the bond to the electrophile is more completely formed, and a substantial positive charge is present on the ring. This results in stronger, more pronounced substituent effects, and therefore high selectivity. The electrophile is much more discerning. This concept is qualitatively reproduced by MO calculations, which show greater stabilization of the ortho and para positions in toluene as an electrophile approaches more closely, resembling that later transition state.
And Hammett correlations, using those rough values, give us a quantitative measure of this transition state position, right? They really put a number to how much a substituent influences the rate.
They absolutely do. The slope of the correlation line between the reaction rate and the plus substituent constants is a direct quantitative indicator of how far along the reaction coordinate the transition state lies. A numerically large negative Ra value, like -13.3 for bromination, suggests a strong substituent effect and implies a late transition state that closely resembles the intermediate, where the positive charge is well developed.
All right.
Conversely, a small negative Ra value, like -2.4 for alkylation, indicates a weak substituent effect and an early transition state. The data presented in the source beautifully confirms this. Halogenation exhibits high selectivity, large Arthur. Nitration and acylation are intermediate, and alkylation shows low selectivity, small f.
And we keep coming back to isotope effects. They keep giving us fresh insights into other aspects of the mechanism, specifically the deprotonation step.
Yes, the kinetic isotope effect, or Ke, is a critical diagnostic. As we discussed, a primary Ke, KHKD1, is the definitive sign that the proton removal from this complex is the rate-determining step, or at least partially rate-determining.
Right, that CH bond breaking.
Exactly. While Kes are seldom observed for nitration and halogenation, where deprotonation is usually incredibly fast, they are seen in other EAS reactions like Friedel-Crafts acylation, sulfonation, nitrisation, and diazocoupling. This tells us that in these reactions, the deprotonation step is slower and has a more significant impact on the overall rate.
And the source notes that only with very weak electrophiles, like in nitrization or diazocoupling, are Kes in the range expected for fully rate-controlling deprotonation.
That's a crucial point. Even for weak electrophiles, some additional factor that significantly retards deprotonation is often required for it to become the sole slow step. For example, in some diazocouplings, steric hindrance from a bulky group near the site of substitution can physically impede the removal of the proton by a base.
Ah, physical blocking.
Exactly. This makes proton removal the rate-limiting step, leading to a strong primary isotope effect, providing unequivocal evidence of its kinetic role.
This is great. The source summarizes all these ideas with 4 possible energy profiles. Can you walk us through those, tying together kinetics and selectivity for us?
Certainly. These profiles are powerful visual summaries that elegantly connect kinetics, selectivity, and the rate-determining step for EAS reactions. Case A represents a scenario where the formation of the electrophile itself is rate-controlling. You diagnose this by observing kinetics that are independent of the aromatic compound's concentration, essentially. The reaction speed is limited by how fast the attacking species is generated, not by how reactive the aromatic ring is.
Okay, the supply bottleneck again.
Right. Case B is when complex formation is rate-controlling, but it involves a non-selective electrophile. This implies an early transition state, which leads to low selectivity. The rate law here would typically depend on both the electrophile and the aromatic compound, but the electrophile wouldn't show much preference between different positions or different aromatic substrates.
The fast and loose case.
Kind of. Case C also has a complex formation as rate controlling, but here it involves a more selective electrophile. This suggests a later transition state, where the positive charge is more developed on the ring, leading to high selectivity. This is where you'd see strong substituent effects, high partial rate factors, and clear directing patterns.
The picky one.
Exactly. And finally, case D, where the proton removal and rearomatization step is rate limiting. This is definitively recognized by the observation of a primary kinetic isotope effect at the site of substitution. This is the smoking gun that tells you the CH bond breaking is the slowest part of the reaction. These 4 cases provide a concise yet comprehensive mechanistic map for understanding the diverse behavior of EAS reactions.
From the relatively simple benzene ring, let's explore how reactivity and regioselectivity change when we move to more complex aromatic systems. What happens in polycyclic aromatic hydrocarbons, or PAHs, like naphthalene or anthracene?
PAH are generally more reactive towards electrophilic aromatic substitution than benzene.
Okay, more reactive. Why?
The primary reason for this enhanced reactivity lies in their lower localization energies for forming that key cationic intermediate, this complex. Think of localization energy as the cost instability that an aromatic ring has to pay when it temporarily breaks its electron cloud to react. A lower cost means the ring is much more willing to react.
Makes sense.
For instance, the localization energy for benzene is a substantial 36.3 kilomole, but for naphthalene, it drops significantly to 15.4 kilomole, and for anthracene, it's even lower at 8.3 kilomole. This means a greater proportion of the initial resonance stabilization energy of the aromatic system is retained in the intermediate, making its formation energetically more favorable.
So they're more willing to disrupt their aromaticity because they don't lose as much stability in the process. What about naphthalene specifically? It's known to show some duality in its reactivity, isn't it?
It absolutely does, which is fascinating. Naphthalene has 2 primary positions for substitution, C1 and C2. Under kinetic control, meaning the reaction that happens fastest, the 1 position is the preferred site for electrophilic attack. This is because the cationic intermediate formed from 1 substitution is significantly more stable. It retains a larger portion of the original resonance energy, benefiting from both allylic and benzylic stabilization. This intermediate forms more quickly.
So it's about the more stable intermediate forming faster. But then you mentioned thermodynamic control.
Yes, under thermodynamic control, when reactions are reversible and allowed to reach equilibrium, typically at elevated temperatures, like in sulfonation reactions, the 2 isomer is often formed preferentially.
Ah, the other position becomes favored.
Right. This indicates that the 2 substituted product is thermodynamically more stable overall, even if it forms slower. An elegant way to demonstrate this kinetic versus thermodynamic control is through deuterium exchange experiments using NMR spectroscopy. You initially observe faster exchange at C1, reflecting kinetic control. But over time, as the reaction equilibrates, the extent of deuteration becomes equal at both positions, clearly confirming that thermodynamic control takes over and that the 2 isomer is the more stable product.
What about larger PAH, like anthracene and phenanthrene? Where do they prefer to react and why?
Both anthracene and phenanthrene react preferentially in their center rings.
The middle one?
Yeah. This behavior is entirely consistent with our understanding of resonance stabilization. The complexes that result from substitution in the center rings of these molecules manage to retain 2 intact benzene rings within their structure. This maximizes the total resonance stabilization of the intermediate, making the formation of these specific intermediates energetically the most favorable pathway. It's a clever way the molecule minimizes the disruption to its overall aromaticity.
And do PAHs ever do anything other than substitution? Do they ever just add things on?
They can, yes.
Yeah.
Notably, phenanthrene and anthracene, especially anthracene, have a tendency to undergo addition reactions under certain EAS conditions, rather than just substitution. For example, in the nitration of anthracene in the presence of hydrochloric acid, an addition product can be isolated. This happens because there's a delicate balance in resonance stabilization that can be regained either by elimination of a proton to form an aromatic ring leading to substitution, or by simple addition, resulting in 2 intact benzene rings, but losing aromaticity in the reacted ring. The energy profiles for these 2 pathways can be quite close, allowing for addition products in some cases.
Moving on from hydrocarbons, what happens when we introduce a heteroatom, an atom other than carbon, into the ring, like in furan, pyrrole, or pyridine? How does that change their reactivity towards electrophiles?
Heteroaromatic compounds can be broadly divided into 2 groups, based on the heteroatom's electronic behavior: excessive and deficient. This distinction hinges on whether the heteroatom essentially acts as an electron donor or acceptor to the aromatic system. Host speaker. Let's start with excessive heteroaromatics, like furan, which has oxygen, pyrrole with nitrogen, and thiophene with sulfur. These are 5-membered rings where the heteroatom oxygen, nitrogen, or sulfur contributes 2 electrons to the aromatic system. This electron contribution makes the ring inherently electron-rich, hence excessive.
Okay, lots of electrons.
Right. You can visualize this by drawing resonance structures where the heteroatom donations electron density into the ring, leading to partial negative charges on the carbon atoms. This increased electron density makes them significantly more reactive towards electrophilic substitution than benzene itself.
And is there a specific order of reactivity among them? Like, is pyrrole more reactive than furan?
Yes, there is. The reactivity order typically follows pyrrole, furan, thiophene.
Yeah.
This order directly reflects the heteroatom's electron donating capacity and the effectiveness of its orbital overlap with the carbon system. Nitrogen, being less electronegative than oxygen, is a better electron donor, and oxygen's 2p orbital generally has better orbital overlap with carbon's 2p orbitals compared to the sulfur's larger, more diffuse 3p orbital.
Makes sense.
As for position selectivity, electrophilic substitution usually occurs at the 2 position more readily than the 3 position. This is because the complex intermediate formed by 2 attack allows for more effective delocalization of the positive charge by the remaining carbon-carbon double bond.
Now, what about the deficient ones, like pyridine? These sound like the exact opposite in terms of electron density.
They are indeed. Rings containing an NCH unit like pyridine are electron deficient and generally deactivated to electrophilic attack. Resonance structures clearly show the electronegative nitrogen withdrawing electron density from the ring, concentrating positive character, especially at the 2 and 4 positions.
Right, the nitrogen pulls the electrons away.
Exactly. Another critical factor in their very low reactivity under many EAS conditions is that the lone pair on the pyridine nitrogen is not part of the aromatic system. It's basic. So under many EAS conditions, the nitrogen will be protonated or complexed with a Lewis acid. This formal positive charge on the nitrogen further enhances the deactivation towards electrophiles, making them even more reluctant to react.
So where do electrophiles attack on pyridine, given how deactivated it is?
For pyridine, the reactivity towards electrophilic substitution is highest at the 3 position, followed by 4 and then 2. The ring nitrogen acts as a strongly destabilizing internal electron-withdrawing substituent. It particularly destabilizes the 2 and 4 intermediates, where the positive charge would directly overlap or be directly adjacent to the positively charged nitrogen atom. The 3 position, while still deactivated compared to benzene, is significantly less affected by the nitrogen's electron withdrawing effect. Hence, it's the preferred, albeit still difficult, site for attack.
This all sounds like it could be tied to something called chemical hardness, a concept you mentioned earlier. What's that connection to EAS?
The concept of chemical hardness is related to the LUMO-HOMO energy gap in a molecular orbital theory. Roughly speaking, a softer reactant, meaning one with a smaller energy gap between its highest occupied molecular orbital and its lowest unoccupied molecular orbital, is generally more reactive because it's easier for an electrophile to complete its bond formation. It's a measure of how easily electrons can be distorted or moved.
And there's a specific term for this in ES, activation hardness.
Correct. Activation hardness, denoted as E delta eta star, is defined as the difference in the LUMO-HOMO gap between the reactant and the cationic intermediate. Qualitatively, a less positive μ value means higher reactivity. The source provides some computational data that generally shows a qualitative agreement with observed reactivity trends within groups. For example, activated benzenes tend to have lower D values for the reactive positions than deactivated ones, making their attack energetically more favorable.
But it's not a perfect predictor across the board, is it? It seems like some theoretical models have their limitations.
That's an important point for your critical thinking as a learner. No, it's not always a perfect predictor. While generally good for predicting position selectivity within a specific structural group, it sometimes fails to accurately predict relative reactivity between different structural groups. For example, some deactivated benzenes, like benzaldehyde, are actually calculated to have lower D values than benzene itself, which contradicts their experimentally observed lower reactivity. Similarly, pyridine's deactivation relative to benzene isn't fully reflected by its D value. However, it does correctly predict the preference for meta-substitution in deactivated benzenes. So, it's a useful tool, but not the only one.
Okay, let's zoom in now and dive into some specific, very common EAS reactions. We'll start with nitration again, but this time we'll go into more detail on its unique aspects.
Absolutely. Nitration is incredibly well studied. To quickly recap, it involved 3 fundamental steps: generation of the electrophile, attack on the ring, and deprotonation. We know the nitronium ion, NO2 plus A, is the key electrophile, and its formation can indeed be the rate-determining step for very reactive aromatics, leading to zero-order kinetics in the aromatic compound.
What's peculiar, though, is the source mentioning that the product distribution for nitration of toluene, meaning the ortho, meta, and para ratios, is virtually invariant, regardless of the nitrating agent used. Why is that strange, and what does it tell us?
It's quite peculiar because you'd expect different nitrating species, with their slightly different characteristics, to have slightly different selectivities, leading to varying ortho.meta.para ratios.
Right. You'd think the conditions would matter more.
Exactly. The fact that the OMP ratio for toluene, around 65.4.33, remains remarkably constant across a wide range of nitrating agents, suggests a common product-forming step, or a common intermediate, that dictates the final selectivity. One compelling interpretation for this is that the final product distribution isn't determined by the initial electrophilic attack, but rather by the collapse of a unique intermediate, a NO2 radical anion bilocation radical pair, formed after an initial electron transfer from the aromatic to the electrophile.
Ah, that electron transfer idea again.
Precisely. At that point, only the NO2 group is in intimate contact with the substrate, essentially locking in the consistent selectivity regardless of how the nitronium ion was originally generated.
So it's not the initial attack, but a later common step that dictates the final product mix. And computational studies actually support this electron transfer idea.
They do. Advanced computer modeling, using techniques like density functional theory, has been used to peer into the interaction of benzene with NO2 plus R. These studies show initial oriented complexes where the NO2 unit is significantly bent, resembling a neutral NO2 molecule rather than the rigid nitronium ion.
Interesting shape change.
Yeah. It strongly suggests that substantial electron transfer has already occurred, forming a radical ion pair. These complexes are only slightly less stable than the full nitrocyclohexadienyllium ion. Furthermore, computational models that account for solvent effects show that the barrier for complex formation decreases dramatically with increasing solvent polarity. In highly polar solvents, this barrier can even become virtually non-existent, which is very consistent with an electron transfer mechanism where charge separation is stabilized by the solvent.
Beyond the classic nitric acid-sulfuric acid mix, what other synthetic variations of nitration are used in the lab or industry?
For a broader perspective on nitration, you should know that chemists have developed several clever alternatives. One common method involves nitric acid in acetic anhydride, which generates acetyl nitrate, CH3CONO2, a potent, often milder, nitrating agent.
Okay.
There's also the even more reactive trifluoroacetyl nitrate, CF3CONO2, formed from nitrate salts and trifluoroacetic anhydride. And for more sustainable or selective nitrations, there are catalytic systems using lanthanide triflates like YbOTF3. These metal catalysts allow for nitration with nitric acid in inert solvents and, crucially, can often be recovered and reused, making the process more efficient and environmentally friendly.
Let's move on to halogenation. What are the key points here for adding halogens like chlorine or bromine to an aromatic ring?
Halogenation involves the substitution of a hydrogen atom by a halogen, and their inherent reactivity increases as you go up the group, I2Br2Cl2F2.
Right, fluorine being the most reactive.
Exactly. For most preparative purposes in the lab, Lewis acids like aluminum chloride, LCl3, or IN3 chloride, FeSO3, are commonly used as catalysts. These form complexes with a halogen molecule, for example, Cl2LCl3, which act as the active, more reactive electrophiles. This complexation weakens the halogen bond and lowers the activation energy for complex formation, accelerating the reaction.
So tell me a bit more about chlorination specifically.
For uncatalyzed chlorination of reactive aromatic compounds, molecular chlorine, Cl2, can be the active electrophile. This reaction is characterized by high selectivity, typically showing a large negative value, around -9 to -10 in Hammett plots, and a high partial rate factor for toluene, Fp equals 820. Both of these indicators point to a late transition state that closely resembles this complex. When catalyzed by Lewis acids, however, the substrate selectivity is often lower, as expected for a more reactive electrophile. Hypochlorous acid, HOCl, is a weak chlorinating agent on its own, but in acidic solutions, it's converted to more active species like dichlorine monoxide, Cl2O, or the protonated form, H2OCl plus micas. The kinetics of these reactions can be quite complex, sometimes with the generation of these more reactive species becoming the rate-limiting step.
And what about bromination? How does it compare?
Molecular bromine, Br2, is generally the active agent in uncatalyzed brominations. Its kinetics can be complex, often influenced by bromide ion concentration, which can shift the rate-determining step from complex formation to deprotonation at high concentrations.
So conditions matter there.
They really do. The electron transfer hypothesis is again prominent here, with both experimental and sophisticated computational evidence supporting a benzene radical occasion Br2 radical anion pair intermediate. Bromination shows very high reactant selectivity, with toluene Fp values around 2500. Significantly higher than nitration.
Wow, that's very selective.
It is. This, coupled with a large negative value, around -12, definitively places its transition state late on the reaction coordinate, meaning substituents have a profound influence on both the reaction rate and the orientation.
What about isotope effects for bromination? You said they're generally rare for nitration, but here...
While generally absent, because deprotonation is usually very fast, kinetic isotope effects are observed in specific, sterically hindered systems, such as highly alkylated benzenes or certain substituted anisals.
Okay, so bulkiness matters.
Exactly. In these cases, the sheer bulk of the substituents can physically impede the removal of the proton, making the deprotonation step rate-limiting. This provides clear, direct evidence of a K and highlights how even a normally fast step can become kinetically significant under specific conditions, proving the mechanistic subtleties we discussed.
That's a great example of how exceptions can confirm the rule, highlighting the mechanistic nuances. And then there are these acyl hypohalites. They sound potent.
Yes, these are incredibly highly reactive halogenating agents. Think of compounds like acetyl hypobromite, CH3CO2Br, or trifluoroacetyl hypobromite, CF3CO2Br. The latter is exceptionally potent, estimated to be a staggering 10 times more reactive than Br2 itself.
10 billion times. Wow.
They're typically formed from hypolous acids or from halogens reacting with mercuric acetate. Their extreme reactivity means they can be the principal halogenating species even when they're present in very low equilibrium concentrations, simply because they react so incredibly fast.
What about the two ends of the halogen spectrum, iodination and fluorination?
Molecular iodine I2 is a very weak halogenating agent. It will only react with highly activated aromatics. To make it more effective, chemists often use iodine monochloride, ICl, catalyzed by Lewis acids, where the iodine acts as the electrophilic part. Acyl hypoiodites are also employed. Fluorination, on the other hand, is notorious for its explosively violent nature, making direct synthesis extremely challenging and dangerous. Mechanistic studies conducted at very low temperatures, where it's safer to control, reveal that fluorine is a very unselective electrophile, with low partial rate factors and a small value. This indicates a very early transition state, consistent with its high reactivity but lack of discernment. For controlled fluorination, specialized reagents like trifluoromethyl hypofluorite, CF3OF, or trifluoroacetyl hypofluorite, CF3CO2F, are typically used.
Moving on to protonation and hydrogen exchange. Here, the proton itself is the active electrophile, which sounds like it simplifies things mechanistically.
It does in a way because the proton is the attacking electrophile. The mechanism is simplified because of the principle of microscopic reversibility, which implies a symmetrical potential energy surface for protonation and deprotonation. We typically track this reversible reaction using isotopic labels like deuterium-D or tritium-T, either by tracking their incorporation into the aromatic ring or their release.
And what do we learn about selectivity here? Do ERGs still activate orthopara positions?
Yes, the familiar pattern holds. Electron-releasing groups, ERGs, activate the ortho and para positions, similar to other EAS reactions. For example, toluene's para partial rate factor, FP, is around 102, meaning the para position of toluene is about 100 times more reactive than a single position on benzene, making toluene itself roughly 300 times more reactive than benzene overall.
Still quite activating.
Definitely. The value of approximately mitigate 8.6 places protonation in the intermediate range of selectivity, similar to what we saw for nitration.
And this is one of those crucial reactions where we do see a clear, definitive isotope effect, right?
Crucially, yes. Hydrogen exchange exhibits general acid catalysis, which is a definitive mechanistic indicator. This means that the rate of the reaction depends not just on the concentration of the strong acid, but also on the concentration of other proton donors present. This observation confirms the proton transfer step is indeed rate-limiting. This, in turn, leads to a substantial primary kinetic isotope effect, with KD values as high as 9.0 being observed for compounds like 1003.5 trimethoxybenzene. This conclusively demonstrates that proton loss is a rate-determining step in these reactions.
Now let's talk about the Friedel-Crafts reaction, starting with alkylation. This is a very important reaction in synthesis, often leading to the formation of carbon-carbon bonds.
Absolutely. Friedel-Crafts alkylation is an incredibly important and versatile method for introducing alkyl groups, those carbon chain substituents, onto aromatic rings. It typically involves generating carbocations or related highly reactive electrophilic species, often from alkyl halides reacting with strong Lewis acid like aluminum chloride, AlZl3, antimony pentafluoride, SbF5, or titanium tetrachloride, TCl4.
Got it.
Alternatively, alcohols or alkenes can serve as sources of these carbocations when treated with strong acids.
It sounds powerful, but the source mentioned the kinetic challenges. Why is it tricky to get precise rate data for these reactions?
It's true. Obtaining precise absolute rate data can be difficult due to several factors. Many Friedel-Crafts reactions are highly sensitive to trace moisture, which can complicate the kinetics. Also, the reactions often involve heterogeneous mixtures, meaning the catalyst might be a solid and the reactants liquids, which makes kinetic analysis challenging.
Right, messy systems.
Pretty much. However, the general mechanism involves three key stages. First, complexation of the alkylating agent with the Lewis acid, sometimes forming a discrete carbocation. Then electrophilic attack of this carbocation on the aromatic to form this complex. And finally, deprotonation to yield the alkylated product.
And what's a signature characteristic of this reaction that strongly points to carbocations as intermediates?
The frequent observation of rearrangement of the alkyl group. This is a telltale sign that a carbocation intermediate is involved.
The group rearranges itself.
Yes. If you start with, say, a primary alkylolide, you might surprisingly end up with a secondary or tertiary alkyl group on the ring, because the initially formed carbocation can undergo a rearrangement, a shift of a hydrogen or an alkyl group, to form a more stable carbocation before it attacks the aromatic ring. Like a classic hallmark of carbocation chemistry.
What about selectivity in Friedel-Crafts alkylation? How picky is this reaction compared to nitration or halogenation?
Alkylation typically exhibits low reactant selectivity, with toluene.benzene reactivity ratios usually between 2 and 25. Positional selectivity is also modest, with ortho and para products often comparable. However, steric effects play a major role here.
Ah, bulkiness again.
Big time. As the size of the entering alkyl group increases from methyl to ethyl to isopropyl, the amount of ortho substitution decreases dramatically. For T-butyl groups, you often see no ortho product at all due to the severe steric hindrance.
So it's not just electronic effects. Big groups don't like tight spaces. And there's also a kinetic versus thermodynamic control issue here, right?
Yes, this is a crucial point for practical synthesis. Strong Lewis acids, used as catalysts for alkylation, can also catalyze the isomerization of alkyl benzenes once they're formed.
Oh, so the products can change after they form.
Exactly. This means that if the reaction is allowed to proceed for too long or at higher temperatures, the product composition you observe might not reflect the initial kinetic selectivity of the electrophilic attack. For example, dialkyl benzenes tend to isomerize to the more thermodynamically stable meta-isomers. So careful experimental control, often by stopping the reaction before equilibrium is reached, is needed to understand and obtain the true kinetic product ratios.
And this reaction has huge industrial relevance, right? It's not just a lab curiosity.
Immense. Think of the industrial production of ethylbenzene, which is a key precursor to styrene, the building block for polystyrene plastics. Ethylbenzene is made by reacting benzene with ethylene, essentially a large-scale Friedel-Crafts alkylation.
Right, for plastic.
Beyond this, milder Lewis acid catalysts like scandium, copper, and lanthanide trifleets are being actively explored for more specific and controlled alkylations, especially those involving stabilized carbocations or secondary sulfonates. These offer more selective and often greener alternatives.
Next up, Friedel-Crafts acylation. How does this compare to alkylation in terms of mechanism and selectivity?
Friedel-Crafts acylation usually involves an acyl halide that's a carboxylic acid derivative with a halogen and a Lewis acid catalyst reacting with the aromatic compound. The key difference from alkylation is the active electrophile. Here, it's typically an acylium ion, a fascinating positively charged species that looks like RCO plus half.
Okay, a different beast entirely.
Right. Alternatively, it can be a complex form between the acyl halide and the Lewis acid. For less reactive aromatics, sometimes a protonated acylium ion or an even more complex species is believed to be the active electrophile.
And there's good evidence for these acylium ions, isn't there? They're not just theoretical.
Absolutely. We have quite compelling evidence. For instance, acyl halides can form 1.1 and 1.2 complexes with Lewis acids like LCl3, and these complexes can be observed by NMR spectroscopy. X-ray crystallography has even allowed scientists to literally see Lewis acids binding to the carbonyl oxygen of acyl halides.
Wow, actual pictures.
Yep. Even more compelling, acylium salts can be generated and exist as stable, isolable entities in non-nucleophilic solvents. Their structures have been definitively confirmed by X-ray diffraction. We have actual crystal structures of, for instance, the acetylium ion. Crucially, the positive charge on these acylium ions is delocalized onto the oxygen atom, which is consistent with the unusually short CO bond lengths, suggesting significant triple bond character. For aryl acylium ions, the positive charge is also delocalized into the attached aromatic ring.
What about the kinetics and selectivity for acylation? How picky is it compared to the alkylation we just discussed?
Acylation generally shows moderate reactant and positional selectivity, which contrasts sharply with alkylation's often low selectivity. Toluene.benzene reactivity ratios are typically in the range of 100 to 200, which is significantly higher than for alkylation.
Okay, more selective than alkylation.
Right. This implies that acylium ions are less reactive electrophiles than the carbocation intermediates in alkylation, leading to a later transition state and thus higher selectivity.
So they're more discriminating about where they attack. And are steric effects still important here, like in alkylation?
Very much so. For the more selective acylium ions, there's often an unusually high selectivity for para-substitution. For example, if you introduce a very bulky 2004-2006 trimethylbenzoyl group, it shows a strong 50.1 preference for the para position over ortho.
50 to 1, that's huge.
It is. Similarly, increasing the branching of an alkyl group on the aromatic ring decreases ortho product formation during benzoylation. The bulkier the groups, the more they steer the incoming acyl group away from crowded positions.
The source also mentions a modest kinetic isotope effect for acylation. Oh, what does that signify about the mechanism?
A modest chi here is significant. It suggests that proton removal isn't much faster than complex formation, and that the formation of this complex might even be reversible under some conditions.
Okay.
This is an important distinction from, say, nitration and halogenation, where deprotonation is usually extremely fast and shows no chi. This subtle chi in acylation suggests that the deprotonation step can contribute to the overall rate, and that bases, for instance, can influence the ortho-para ratios by affecting the relative rates of deprotonation from different isomeric complexes. Steric effects on deprotonation have also been observed, for example, in the acylation of naphthalene.
And there's an ongoing search for true catalysts in acylation, right? Meaning catalysts that aren't consumed in the reaction.
Exactly. While traditional Lewis acids like LCl3 are often consumed in stoichiometric amounts due to strong complexation with the ketone product, there's a strong interest in finding catalytic systems that aren't. Lanthanide triflates, such as hafnium triflate, HFO3SCF32, lithium perchlorate, and scandium trislate, have shown considerable success as true catalysts. They are presumed to work through aroyl triflate intermediates, which are more easily displaced from the catalyst.
Moving on to aromatic substitution by diazonium ions. These are classified as weak electrophiles, so I imagine they're very selective and only react with certain types of aromatic compounds.
Exactly. Aryl diazonium ions, RRN2+, are indeed a class of weak electrophiles. This means they are quite particular about who they react with. They will only react with highly activated aromatic compounds, specifically those with very strong electron-releasing groups, ERGs, such as anilines, or even more effectively phenylenanions, where the deprotonated oxygen group is an even better electron donor than the neutral hydroxyl.
So only the really reactive rings.
Pretty much. The reactivity of the diazonium ion itself also depends on its substituents. Electron withdrawing groups on the diazonium ion increase its electrophilicity and thus its reactivity, while electron-releasing groups decrease it.
And here's another key mechanistic feature. Rate-determining proton loss? This seems like a rare find in ESS.
It is a crucial and relatively rare mechanistic feature for EAS reactions. In some cases, particularly diazonium couplings involving naphthalene sulfonate ions, proton loss can be definitively demonstrated to be the rate-determining step.
How do they show that?
This is revealed by two key pieces of evidence. First, the observation of a primary kinetic isotope effect, KD in the range of 4-6, when deuterium is present at the substitution site. And second, by the observation of general base catalysis, meaning the reaction rate depends on the concentration of various bases present, not just the solvent or a single strong base. These are direct proofs that the CH bond cleavage is the slowest, rate-determining step for these specific reactions.
Finally, let's explore something called ipso substitution. What exactly is that and why is it important?
Ipso substitution is a fascinating variation where the electrophile attacks a carbon that is already bearing a substituent, Y, not just a hydrogen atom. Think of it as hitting an already occupied spot on the aromatic ring.
Okay, attacking a non-hydrogen spot.
Right. The key condition for this displacement to occur is that the substituent being replaced must be able to leave as a positively charged species, Y+, or be lost in some other energetically favorable way from the intermediate during the re-aromatization step.
So the displaced group effectively leaves as a positive species. Can you give us some examples of what kind of groups can be replaced this way?
Certainly. One type involves the cleavage of highly branched alkyl substituents. For instance, in the nitration of 1,4-bisopropyl benzene or the bromination of 1,33O5-tritibutyl benzene, the bulky isopropyl or T-butyl groups can be expelled as stable carbocations.
They just pop off.
Pretty much. Sometimes dealkylation occurs as a side product, but in certain cases it can even become the principal product of the reaction.
What about halogens? Can they be displaced in an ipso substitution?
Yes, under specific conditions. The replacement of bromine and iodine has been observed during aromatic nitration. For example, nitration of p-brominazole or p-idoinazole can lead to p-nitroanazole, where the halogen is replaced by the nitro group. However, chlorine is less likely to be displaced due to its greater resistance to being eliminated as a positively charged species, reflecting its higher electronegativity and a stronger CCl bond.
And you mentioned a most general and synthetically useful example. What's that?
That would be the electrophilic substitution of aryl silanes, where the trialkyl silane group, R3, is replaced by an electrophile. The silane group is a powerful ipso-directing group.
Why silicon?
This is due to the polarity of the carbon-silicon bond, which makes the substituted position relatively electron-rich, and silicon's unique ability to stabilize positive charge, specifically Becker carbocation character, in the intermediate. The silane group is then easily removed from the complex, likely via a pentavalent silicon species reacting with a nucleophile. These reactions are incredibly fast and occur under very mild conditions, making them attractive for specialized applications, such as the gentle introduction of radioactive iodine for tracer studies in medicine or research.
And trial kill stand-ins are similar?
Yes, trial-Kilton substituents, or SNR3, are also powerful ipso-directing groups. They exhibit similar electronic effects to silanes, but being even more metallic and less electronegative, they increase electron density at the carbon to which they are attached even more effectively. The acidic cleavage of aryl stand-ins proceeds analogously via an ipso-oriented complex, highlighting their utility in precise organic transformations.
Now, we spent a lot of time on electrophilic aromatic substitution, which happens when an electrophile, an electron-loving species, attacks an electron-rich aromatic ring. But what about the opposite? Nucleophilic aromatic substitution, or SNAr. I imagine it's quite different because the ring is already rich in electrons.
You're absolutely right. It's a completely different ballgame. The typical substitution mechanisms we see in saturated compounds like SN1 and SN2 are simply not viable for substitution on aromatic rings.
Why not?
For SN2, a backside attack is geometrically impossible because this sp2 orbital on the carbon atom is directed inward, right into the ring, blocking any approach from behind.
Okay, no room.
And for SN1, forming an aromatic cation, a positive charge directly on a benzene ring is energetically prohibitive. It's incredibly unstable, even less stable than a primary carbocation. This is due to the geometry and hybridization, as the positive charge would be localized in an sp2 orbital that's orthogonal or perpendicular to the system, preventing any stabilizing delocalization of the positive charge.
So, since the classic mechanisms don't work, how does nucleophilic aromatic substitution happen then? What are the viable pathways?
There are two major pathways by which net nucleophilic aromatic substitution can occur. The first is the addition-elimination mechanism, and the second, which involves a fascinating intermediate, is the elimination-addition mechanism.
Let's start with addition-elimination, which involves something called Meisenheimer complexes. This sounds like the core idea here.
It is. This mechanism involves two main steps. First, an initial addition of the nucleophile to a vacant orbital of the aromatic ring, forming a crucial intermediate. Then, this is followed by the expulsion of the leaving group. That key anionic addition intermediate is what we call a Meisenheimer complex. It's electronically similar to a pentadenyl anion, where the negative charge is delocalized over several atoms.
And these Meisenheimer complexes, the source says, are strongly stabilized by electron withdrawing groups, EWGs, particularly when they are located ortho or para to the substitution site. Why is that so important?
It's absolutely critical. These EWGs can effectively delocalize and spread out the negative charge that develops in the Meisenheimer intermediate. Without these EWGs, nucleophilic aromatic substitution is an energetically very demanding reaction, and it typically only occurs under extreme conditions because the initial addition process temporarily disrupts the stabilizing aromatic system, creating a high-energy intermediate.
Right, you need those EWGs to handle the extra negative charge.
Exactly. Powerful EWGs like nitro groups are most effective at stabilizing this intermediate, but cyano and carbonyl groups also work well.
And you mentioned they can actually be detected, sometimes even isolated. That's really seeing the mechanism in action.
Yes. Meisenheimer complexes are often strongly colored, making them spectroscopically detectable using UVVs or NMR. And in some remarkable cases, particularly when they are highly stabilized by multiple strong nitro groups, they can even be isolated as stable salts. This direct observation provides very strong evidence for their crucial role as intermediates in this mechanism.
What's truly counterintuitive about this mechanism is the leaving group ability. It's the opposite of what we'd expect for SN1 or SN2 reactions. In those, iodine is typically the best leaving group, but here the order is often SCl-BRI. Why is fluorine so good at leaving in this scenario?
You've hit on a key difference, and it's a fantastic aha moment. In SN1-SN2 reactions, the ease of bond breaking dictates leaving group ability, IBRCLF, based on bond strength. But in nucleophilic aromatic substitution, the formation of the addition intermediate is usually the rate-determining step, not the bond breaking itself.
Ah, okay.
Yeah.
So bond strength isn't the key factor for the rate.
Exactly. Instead, it's the polar effect of the halogen. The more electronegative halogens, like fluorine, have stronger bond poles that make the carbon atom to which they are attached more electron deficient. This makes that carbon more receptive to the initial nucleophilic addition step, thus accelerating the overall reaction.
So even though the carbon-fluorine bond is the strongest, fluorine is actually the best leaving group in this reaction because it helps the nucleophile get in during the slow step. That's truly fascinating, and computational studies confirm this.
They do. Gas phase computational studies corroborate this counterintuitive order. For example, while the fluoride exchange reaction is calculated to proceed through a stable intermediate with a low barrier, the calculated barriers for direct chloride, bromide, and iodide exchange are much higher.
Yeah.
And critically, the addition of strong nitro groups drastically lowers these barriers, further emphasizing the crucial role of EWGs in making this reaction feasible and efficient.
Can other groups besides halogens be displaced in this way?
Yes. Even groups usually considered poor leaving groups in SN2 reactions like alkoxy groups, nitro groups, and sulfonyl groups can be displaced if strong EWGs are present on the ring. Again, this is because the rate-determining step is the initial nucleophilic addition, and the leaving group is expelled in the subsequent energetically favorable re-aromatization step. A wide range of nucleophiles can participate, including alkoxides, phenoxides, sulfides, fluoride ion, various amines, and even some carbanions. Solvent effects are also very important. Dipolar aprotic solvents like DMSO or DMF, crown ethers, and phase transfer catalysts can significantly enhance reaction rates by providing naked, highly reactive nucleophiles that are less solvated and thus more nucleophilic.
And this reaction has historical significance too.
Absolutely. One of the most historically significant examples is Frederick Sanger's groundbreaking use of 2,4-dinitrofluorobenzene. He employed this reaction to identify the N-terminal amino acid in proteins, which was a pivotal step and fundamentally revolutionized the field of protein sequencing. It truly showcased the practical power of this mechanism.
And how do heterocyclic systems like pyridines behave here? Are they good substrates for a nucleophilic substitution?
They are excellent substrates. Deficient nitrogen heterocycles, such as 2 halopyridines, 2 haloquinolines, and 1 haloisoquinolans, are very reactive towards nucleophilic aromatic substitution. This is because the electron withdrawing effect of the ring nitrogen, which is part of the aromatic system and already pulls electron density, effectively activates the carbon to nucleophilic attack, making them very susceptible to this type of reaction.
What about the other major pathway for nucleophilic aromatic substitution? The elimination-addition mechanism. And this one involves a famous elusive intermediate, right?
It does. This mechanism proceeds through the formation of a highly unstable, transient, and quite fascinating intermediate known as benzyne or dihydrobenzene. It's a species that was hypothesized long before it could ever be detected.
And a key characteristic of this mechanism is the product pattern, which seems a bit weird. It's not straightforward like the other substitutions we've discussed.
It's very distinctive, and it's the signature of the benzyne intermediate. Because benzene essentially has a strained triple bond within the aromatic ring, the incoming nucleophile does not necessarily add back to the carbon from which the leaving group originally departed. It can add to either of the two triply bound carbons.
Ah, so you can get a mixture.
Often, yes. This frequently leads to a mixture of positional isomers in the product, which is a key diagnostic feature for the involvement of a benzyne intermediate. If you see products where the new group isn't where the old one was, benzyne is probably involved.
Can we actually see benzyne, or is it too fleeting?
It's incredibly elusive but not invisible. Benzyne can be observed spectroscopically in inert matrices at very low temperatures, typically generated photolytically. Its bonding is quite unique. It's considered similar to benzene, but with an additional weak bond in the plane of the ring, formed by the overlap of two sp2 orbitals. This makes it strained, but still largely retains its aromatic character.
What's the definitive evidence for benzyne's existence, the experiment that really sealed the deal?
The classic 14C labeling experiment. In this ingenious study, scientists reacted chlorobenzene that was labeled with radioactive carbon-14 at a specific position with potassium amide, a very strong base. When they analyzed the aniline product, the 14C label was found to be distributed between the original carbon and the ortho position.
Split between the two spots.
Exactly. This precise distribution is consistent only with a symmetrical benzyne intermediate, where the carbons involved in the triple bond become equivalent before the nucleophile adds. This provided irrefutable proof of its transient existence.
And what factors facilitate this elimination-addition mechanism? What makes it happen?
The elimination-addition mechanism is primarily facilitated by structural features that promote the removal of an orthohydrogen from the ring by a strong base. The initial step is often the deprotonation of an orthohydrogen, followed by elimination of the leaving group. The halide reactivity order with strong bases like KNH2 and liquid ammonia is generally BRICLF.
Okay, bromine is best there.
Right. This order is interpreted as a delicate balance between the ease of proton removal, which would favor FCl-BRI due to fluorine's electron withdrawing effect, making the orthohydrogen more acidic, and the leaving group ability, which favors IBrClF due to bond strengths. However, with organometallic bases and aprotic solvents, the acidity of the orthohydrogen becomes even more dominant, sometimes leading to a reversal of the order to FCl-BRI.
So how do chemists generate benzyne for preparative work, given how unstable it is? It sounds like you can't just buy it in a bottle.
You certainly can't. But chemists have devised several more convenient laboratory methods for generating benzyne in situ, meaning it's formed right in the reaction mixture as needed. One common and elegant approach involves the diazotization of O-aminobenzoic acids, where a concerted loss of nitrogen, N2, and carbon dioxide, CO2, follows the diazotization, cleanly generating benzyne. Other methods include the oxidation of 1-aminobenzotriazole, which decomposes with the loss of 2 molecules of nitrogen under mild conditions, or the decomposition of benzothiodiazole, a 1,1-dioxide, which eliminates sulfur dioxide, SO2, and nitrogen. These methods allow chemists to harness benzyne's reactivity without needing to isolate it.
And what's benzyne's fate? If there's nothing else around to react with, does it just sit there?
No, it's far too reactive. Benzyne is incredibly transient. In the absence of other nucleophiles or reactive unsaturated compounds, it readily dimerizes, meaning 2 benzyne molecules react with each other to form biphenyline, a larger polycyclic aromatic. Its estimated lifetime in solution near room temperature is only a few seconds, which tells you how fleeting and reactive this intermediate truly is.
Wow. We've really covered a lot of ground today. From the foundational electrophilic aromatic substitution, which adds new groups to electron-rich rings, to the fascinating, sometimes counterintuitive nucleophilic aromatic substitution, which happens on electron-deficient rings or via that elusive benzyne. It's remarkable how seemingly simple transformations in organic chemistry hide such intricate mechanistic details, influenced by everything from subtle electron effects and orbital overlap to the exact position of a single atom.
Indeed. Understanding these underlying principles transforms what might appear to be complex, disconnected reactions into logical, interconnected sequences. This deep dive should equip you with a much deeper appreciation for organic reactivity and a more informed perspective on how molecules are synthesized and analyzed in the real world. It's about moving beyond rote memorization to truly understanding the why behind these chemical transformations.
Absolutely. And as we wrap up this deep dive, consider this. From fine-tuning drug synthesis to designing new materials with specific properties, understanding these subtle differences in how molecules interact is absolutely key. Given the surprising depths we've uncovered in aromatic substitution, what other classic reactions in chemistry might reveal similarly complex and fascinating mechanisms just waiting for your deeper dive? How might this foundational understanding of electron flow and intermediate stability empower you to anticipate and even design new chemical transformations?
It's a vast field full of hidden mechanisms and elegant solutions, and the more we delve, the more we realize how interconnected everything is.
Thank you for joining us on this enlightening deep dive into the heart of organic reactivity. We hope you feel more informed and intrigued than ever.